now you are hopefully persuaded that Byzantine failure model is interesting and worth considering from the practical perspective. So let's see how we can actually develop algorithms for this model. So we start from listing the environment assumptions as usual. So we will consider the model that is called fail arbitrary or fail silent arbitrary. So in this model we have an asynchronous system, so there are no any timing assumptions that we can make on the message delivery time or relative process speed. We have Byzantine processes, the process that can fail by experiencing a Byzantine failure. And we have what is called authenticated perfect point-to-point links. Okay, so we will discuss what it is in slightly more detail in the next slide. But for now, you can just think about it as a weaker variant of perfect point-to-point links that we have already discussed. So one important remark is that in the Byzantine failure model, we typically don't consider failure detectors. And this is because failure detection in this model is infeasible. And the reason for that is that there are simply just too many ways in which a Byzantine process may deviate from a correct behavior. And even more important is that these deviations are actually protocol or algorithm dependent. So we can't have something generic that, for example, just relies on heartbeats to detect failures, as it is the case for crash faulty processes. So in particular, a Byzantine process may reply to all heartbeats but still behave in an incorrect fashion. So what are the authenticated perfect links that we just mentioned? So the reason we need to define a different type of communication channels is that the no creation property supported by perfect channels and other types of channels that we discussed is simply too strong in the presence of Byzantine failures. And this is for the reason that a Byzantine process can actually easily create messages pretending them to be from other processes. So we can't just say that that is impossible, because Byzantine behavior inherently allows this kind of attacks. So to deal with that, we replace the no creation property with something that we call authenticity. And this is also the terminology used in the textbook. So authenticated perfect point-to-point links satisfy the same reliable delivery and no duplication properties as the perfect links do. And in addition, instead of no creation, we have the authenticity property that says that if some correct process Q delivers a message with sender P, and this sender P is correct, then M was actually previously sent to Q by P. Okay, so that means that a process can always authenticate who the sender is of the received messages, provided the sender is correct. So in practical implementations, authenticity is normally supported by means of various cryptographic primitives. So the collective name for them is message authentication codes, or MACs. So MACs are typically implemented using shared symmetric keys, and shared symmetric keys are established through the key exchange schemes, which typically employ public-private keys. So you can find more details if you are interested in section 2.3.2 in the textbook, but for our discussion, it will be sufficient to just assume that this authenticity property is satisfied by the channels. So in the textbook, you also have a simple algorithm that implement authenticated point-to-point links and using the cryptographic primitives such as MUX. And this algorithm is called authenticate and filter, so feel free to explore on your own.